Hi everyone, I'd like to talk about aggregated spatial data. Aggregated spatial data, such as demographic data, is often reported at specific geographic scales, such as a national scale, state, county, or some other administrative division. The US Census collects demographic data about individuals and then reports that data at various scales of aggregation, such as a block group, census tract, zip code tabulation area, and so on. But not all data is available at multiple scales. Interpolation involves taking data available at a specific geographic scale and estimating its value at a desired geographic scale. Let's look at a use case. Imagine you are planning to construct a composite index using spatial data. The composite index will give you a single score derived from multiple inputs for a given geographic level. Perhaps you'll use this index to rank geographies and decide how to allocate resources. Maybe it tells you which neighborhood needs more investment. Many of the data points you may want will be available at a specific geographic scale, such as census tract. However, some of the data you want are only available at a different geographic scale, such as a school district or police precinct. One approach to including the measure that is only available at a different scale is to generalize data from one scale to another through interpolation. Here's how it works. If you have A and B geographies where you want to report data, but the data are reported at another similar scale that overlaps, let's call this area Area C, you can use interpolation to generalize data reported in Area C based on the overlap with areas A and B. The interpolation might be based on a percent of geographic area alone, or it could be proportional to other factors like population. Let's apply some hypothetical numbers to show this in action. Let's say Area C is a measurement of students living in a school boundary, and there are 500 students that go to an elementary school in Area C. We could assign approximately 350 of these students to Area B based on the proportion of area, assign 60 students to Area A, and 90 students to other unmentioned geographies. That's the basic idea. A typical use case might be taking data reported by a school district or police precinct and combining it with data tabulated at either a census tract or zip code level. This technique is best with similar sized geographies that mostly overlap and usually should only be used if you have no other option for accessing data at a common geography. You wouldn't want to use this approach to combine data from a much larger geography to a much smaller geography. For example, it wouldn't make sense to take data reported at a state level and generalize it to a census tract or zip code level. One other fairly common type of interpolation is based on Euclidean distance of point-based objects. In this case, it would be measuring the distance from the centroid of A and B to some other geographic point. This form of interpolation values how far something is from something else. The distance to an object is the value assigned to the geography. Sometimes instead of Euclidean distance, you might measure walking distance, commuting distance, or driving distance. A typical use might be measuring the distance to the nearest public park. The proximity to a public park would have a positive value. Values don't have to be positive, though. For example, if we were measuring the distance to the nearest toxic waste site, proximity would obviously carry a negative value. If you are measuring the Euclidean distance of multiple point-based objects, it is important to accurately represent the relative qualities of those points. To exemplify, let's return to thinking about the distance to the nearest public park. Let's say you want to see which geography has a better proximity to a park. A and B are both equal distance from a park, yet not all parks are created equal. The recreational possibilities can vary between an urban pocket park and, say, an expansive regional park. Attributes such as size, recreation options, open hours, availability of transit are all factors to consider in this kind of analysis. As a data consumer, you ought to be critical whenever you come across reports that seem to use interpolation. If an organization boasts about equal access to some service across the city, they might say something like, 90% of residents are within walking distance to a local park or a local library, or fill in the blank with some other service. You should be asking what factors were included and excluded in those statements, and determine if something important has been overlooked. Aggregation also creates a spatial problem where our interpretation is malleable based on geographic constructs. Spatial data can be concentrated in a specific area. There is the modifiable areal unit problem, or MOP. MOP has real-world consequences for how aggregated geospatial data is reported. The one-sentence summary is that if you partition your aggregated spatial data in a different zone or scale, you can achieve a different mapped outcome. I like this graphic, which shows 3 individuals. 2 of them are well, 1 of them is sick. Depending on how the spatial boundaries are set in the aggregation on the bottom, parts of the same area can be described as having an illness rate of 0%, 50%, or 100%. In another example, Canadian geographer Nadine Sherman took a couple different health indices and mapped them at different geographic scales. As the scales changed from smaller geographic areas to larger ones, the map produced outputs that were shaded differently. Geographic analysis choices can change your end results. Interpolation should be used cautiously so as not to exacerbate aggregation issues. Like with other forms of visualization, you should include documentation. Some examples of documentation to include are a non-technical summary of derived insights, lineage of the individual indicators, and resources to help people replicate what you've done.